last lecture we got the equations for a beam bending vibration with the mass at the one end, and we got this equation after the separation of variables. Please note. Okay. Along with boundary conditions, at x equals 0 we had two boundary conditions, which is EI is 0, and then another boundary condition is ML omega square W minus d over dx of EI d equals 0, and then at x equals L, that is the other end, we had EI d square W by dx square equals 0 and d over dx of EI. So these are the four boundary conditions. You got that. So we are continuing from here. But you look at the form of the boundary conditions. In three boundary conditions, you had the homogeneous, right side is 0. Whereas in one boundary condition, there is a omega sitting in, which is again sitting in the field equation. Okay. Whereas that is why, depending on the problem, the omega can be in the boundary condition or it need not be in the boundary condition. And again, the boundary conditions are split into two types of boundary conditions. One is called the I'll write boundary conditions types, that is geometric boundary condition, and another one is natural or force boundary conditions. Okay. Again, it depends on the type of problem you are dealing with. In the current case, all the boundary conditions are natural force type. Whereas if you have a fixity, like a cantilever beam, one end is fixed, or if it is a simply supported, those may provide geometric boundary conditions, in which basically displacement and slope. That's why again the boundary conditions are split, and if you look at the highest order of the differentiation in the boundary condition, no, here you have to have, okay, it is a order 3, okay, and whereas this is fourth order equation, because we have already done the separation of variable and W is only a function of x. So this is an ordinary differential equation with boundary condition. So our aim is to obtain the solution which is actually omega as well as w, which is a function of x. Now, one value is if you set w equal to 0, then everything will be satisfied. That is a trivial solution. That means nothing is happening to the beam. But the aim is to find out for what values of omega which are non-zero you have solutions, okay, where you will have w a function of x. This is what the whole differential eigenvalue problem is this. All types of differential eigenvalue problem. But there is a class of problem which is actually written as, I'll just briefly mention and I will not get into the details of that. That is the order 2. This is order 4. This is boundary value problem. Okay. The differential equation is given like this: d over dx of p of x dy over dx plus q of x plus lambda r of x y equals 0 in the zone x in the domain. Here this is valid in the domain x L L 0 because this is where it is valid. This is the domain, and at the end you have the boundary condition. Now, with the boundary condition with BC are given a1 y of a plus a2 y prime of a equals 0, and similarly b1 y of b plus b2 y prime of b equals 0. This is the form of the boundary condition, but please understand this is like one set of boundary condition, it is only referred to one end A, the other one only B. So they call it separated boundary condition. And if you look at for this type of problems, there are some conditions are also put in, that is P of x, I'll write it here, with P of x greater than 0 and R of x also greater than 0. And these are all constants, A1, A2, B1, B2, they are all constants. Okay. Essentially, this problem goes towards solving the value of lambda and your y. For what values of lambda you have a solution, and it says, because it can be proven later, because that is where the self adjointness, everything, I will try to derive it in a general form. It says that we will have these values, the eigen values you may call it. They will take lambda 1, lambda 2, so on. You can have lambda n, etc. Corresponding to that you will have the solution, which is, you call it, this is eigen values, and there are eigen functions, okay, which are phi 1 Pn. These are functions of y and so on. Okay. You will have infinite, but infinite doesn't mean it is a, you can count. That is why you will say countably infinite eigen values. Correspondingly, you will have eigen functions. Okay, and they satisfy, and these are all real numbers. Please understand, real numbers, lambda 1 to lambda, and they satisfy the condition that the interval a to b r of x p m, sorry, not y, these are all of x. I'm sorry about that. This is about x because we have our variable is x. Okay. This is equal to 0 if m is n. Okay. These are, I'm just giving only what is from a math material. I'm just writing, this is the Sturm-Liouville theorem and what it gives. What is the equation, boundary condition, the conditions on p of x, r of x, and the solution will be what type and what they satisfy. Okay. This is just for your information. Now we leave that part. We will go to our, because you will find that torsion problem will be second order. This is the fourth order. Okay, torsion problem will be second order. So we try to generalize all these situations and then write it in simply operator form. Okay, and then get the full approach. Why this is valid? All this proof we will give various things. Okay. After that, we will continue with our vibration problem. Okay, of a beam. So we take the entire L. Let us write the equations. L W equals omega square m W, and then Bi is 0, and then another Bi W equals omega square Ci, and here I running from 1 to k, and this is I running from k plus 1 to p, but you can say x 0 and L 0 and L, because you have to satisfy these boundary conditions. L is a linear differential operator. This is linear operator of order 2p, where p is 1, 2, etc. integer. Here these are maximum order BIs is order 2p minus 1 maximum. Okay. Similarly, you can have M also a differential operator, okay, of order q. We will say order 2q, we will write it, and this will be order 2q minus 1. But please note that P is greater than Q. Okay. But normally for our, if you have a tip mass, we didn't have any differential operator because there was no difference. But where will you get the differential operator? Suppose in this situation, tip mass, or we didn't allow any, that mass is distributed mass we took. Here also you may get some differential operator sometime. That's why I am saying tip mass goes here. The distributed mass, you put it as a mass. Suppose if you add rotation, that is rotary inertia of the elemental mass, and take its kinetic energy. That means we took only half m w dot square. You can also take some inertia into w prime, which is dw by dx, that is the rotation, its time derivative as a dot, one more dot. Then it is like rotary inertia. If you take, then you will get a differential operator here. Okay. But most of the problems what we deal with, it's like a only mass, 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 without taking rotary inertia. We will not get a differential operator in this case here. Okay. Same thing to this also. Now this is our general problem. We define, our idea is what? We need to get the solution omega square and w, which is a function of x. There are different types of functions. We will first define them, like admissible functions. Okay. What are admissible functions? These are functions, that is arbitrary functions. Please note, arbitrary functions satisfying only geometric boundary conditions. Geometric boundary conditions. Okay, only geometric boundary conditions. You can knock it out if you want. Then you can have comparison functions. Okay. These are again arbitrary functions satisfying all boundary conditions, all, that is both geometric and natural. Okay. BCs. Now, if I just to bring out the distinction, I said here it satisfies only geometric boundary conditions. Okay. Here I am saying both geometric and natural. We saw that the natural boundary conditions, the order of derivative will be 2p minus 1. That means they must be, sorry, 2p, not minus 1, I could say they should, because 2p times differentiable. Let us put it that way. 2p times differentiable. This one, if they satisfy only geometric displacement and slope, the condition on this is you put it only p times differentiable. Okay. Differentiable means differentiable over the domain, because you should, because at the end geometric boundary condition you may say displacement is 0, slope is 0. Okay. And why the p times 2p times differentiable, that will become obvious when we solve problems, because we said that this is 2p times differentiable operator. If you want to substitute that function, it should be possible to go for 2p times differentiable. Otherwise, if it is less differentiable, it will be 0. There is no solution. But admissible function, we will not be putting it here, because it is only p times differentiable. You cannot put them here. Then what for we are defining, you will understand. If there is a way of, if I modify this into another form, the energy form, if I write it, then I find the function has to be only p times differentiable. I don't need to go for 2p times, but these are all approximations. Then there is a last one, which is actually, these are admissible function, comparison function, and then eigen function. Okay. These are 2p times differentiable. Okay. And then satisfy all boundary conditions and also the equation that is important, because they satisfy the equation also. Okay. That means that is the exact solution. Okay. Because they satisfy all boundary conditions and also the equation, everything. Whereas here, I don't insist that comparison function, they should be 2p times differentiable. They satisfy both geometric and natural boundary conditions. Here I say they satisfy only geometric boundary conditions. Whereas here I say all boundary conditions, also the equation. Okay. Now the problem is, it's not easy to get eigenfunctions for all problems. Okay. It is not easy to get. Therefore, you have to, the whole analysis or the solution technique is, what is the best way, the approximate procedure, so that you can get a good solution. That's all. So the entire study goes towards obtaining approximate solutions. All right. Exact solution is possible only for highly specialized cases. Very few cases you can have. Now we will define if, we will not get into this. You have understood these three types of functions. Now we will use, wherever I say comparison function, that means you immediately know, that means it satisfies the boundary condition 2p times differential. If I say eigenfunction, it satisfies the equation also, because eigenfunctions have certain properties. Those properties have to be mentioned, like orthogonality or something will come. That we have to prove it. And these operators are, what type of operators they are? Okay, because if they follow certain class, then you say my solution should be of this type. Okay, that is what you will learn. Now, let us take we call self-adjoint system, and there is a conservative. Please understand, there is no damping, dissipation, nothing. Whatever work that done, that goes into the strain energy, and this is a free vibration problem. Please understand, this is a free vibration because we don't have any forcing function. Okay, so this is a conservative system, and self-adjoint systems. What is the meaning of this? And they are also, we'll say, positive definite. There are two words I am introducing: self-adjoint system and then positive definite. Okay. This is a linear conservative system. That's all. You can say conservative system because there is no dissipation, and whatever work you do, the inertia and potential strain energy. So there is an interplay, like your simple vibration problem. Only thing is, this is a distributed system, continuous system. Now, if let us consider 2p times differentiable comparison functions. Okay. What do we mean by adjoint? Okay, we have to define what adjoint means. If comparison function satisfy, okay, we are taking some functions which, of course, they are all comparison functions. If they satisfy this is D is a domain. Okay, that means domain the field. In the case of beam, 0 to L, length of the beam, and this U, this is the operator L. This operator operates on V, okay, and U and V are comparison functions. Plus you put summation I running from K plus 1 to P. This is over a surface. Surface means only end point, that is the boundary. You will have U, B, I, V, D surface. This is equal to domain V, L, U, D, D plus summation I running from K plus 1 to P over the surface V, B, I, U, D. So you see what is happening is ULV plus this B I k plus 1 to p, that is only this. This is not considered, okay, only this condition. You follow? Where there is those boundary conditions which are having omega square in their relationship. Okay. If this is satisfied, that means U and V are any two arbitrary comparison functions. If this is satisfied, then L is self-adjoint. Okay. But now you see most of the, that is why I wrote this particular thing was, if my boundary conditions are of this type, okay, I will simply get, that means all are there, omega does not appear in the boundary condition, then self-adjointness becomes simply U L V D D equals, this is what, V L U over the domain. This is what will happen, because these two are not there. And many times, most of the books, because if you don't consider that type of boundary condition at all, you will tend to think that this is what the self-adjointness is. Okay. That is why I just put one mass extra on the beam and show that how that comes as a boundary condition, and then how this is also has to be considered. Similarly, for the mass means that capital M, you also have the self-adjointness. This is you call it, because this goes to stiffness term. This is omega square, this is the mass term. So you can say this is a stiffness operator, this you can call it mass operator. Okay, but anyway that equation also will look like this. That is D U capital M V, but here you add only the other condition, k plus 1 to P ds equals V capital M U dd plus summation I running from k plus 1 to P V C I U d s. Okay. Suppose if you say the stiffness operator, stiffness, and this is a mass operator, you may call it. If these two are self-adjoint, okay, then you say my problem is self-adjoint. Followed. And as a matter of fact, this can be written, if you actually, what you have to do, I am only describing in words, I am not going to derive that. If you take only this part or that part, you essentially, the differential operator is operating on V. What you do is you integrate by parts, once, twice, something like that, depending on the order of your this. Okay. Then what will happen is this will become quadratic in form. if it becomes quadratic in form, then you can change u or v wherever they interchange. It doesn't matter, the expression will remain the same expression. Okay, that is why sometimes this itself is written, but you should have the boundary condition, so that when you integrate by parts, what happens? You are going to get the boundary condition. Okay, that is why when the boundary conditions are 0, you don't need this. Whereas if they are not 0, like 0 means not homogeneous, like you have a omega square sitting there, then you need to have the term sitting there. Okay, and if you have that form, then this is a self-adjoint. Wherever you cannot get it in that form, if it is not valid, then it is not a self-adjoint operator. Okay. Now the question is, if it is self-adjoint, okay, you have a well set procedure for obtaining the solution. But if it is non-self-adjoint, what you do? That's another case. Okay, that we will talk about that later. First we will say only self-adjoint part. You follow? So in the self-adjoint, our problem is self-adjoint, and I just leave it like this because I am not going to put it in a form, because when we get the example, what I can do is I can take the example which we derived, whatever that beam with the one end mass, we do the same thing. We can apply that, okay, and then show that. Maybe that you can take it as an exercise for yourself. For that problem, with those boundary conditions, show that is self-adjoint. Okay, this is like an exercise for you. I leave it to you. Okay. Now, another thing is, maybe I can erase this. For any comparison function u, please understand, for any comparison function u, I am putting it like this, u, I am putting same u. Any comparison function, please understand, but that is the key. That is why 2p terms differentiable comparison function is essential. If this is always greater than 0, okay, then the system is positive definite. Only when u is 0, it is equal to 0. You follow? On the other hand, if for some u, okay, it is equal to 0. So greater than 0 is positive definite. Okay, why I put equality here also? Greater than or equal means positive semi-definite system. Positive, that is called semi-definite system. In this case, even for non-zero u, it may be equal to 0. Okay, that's all. So positive definite, semi-definite. Okay, these are in this is in differential operator form. Actually, if you see what is the analogy in matrices, because you have learned spring mass damper, spring mass system, damper you leave it. If you want to find out the stiffness matrix, mass matrix, there the stiffness matrix, if it is symmetric, you say, and mass matrix symmetric. That symmetry goes towards self adjoint. Okay, whereas adjoint is A transpose is A. Okay, so if it is a symmetric matrix, mass matrix, stiffness matrix, you say self adjoint. Then what is the positive definite comes? Then normally you take any vector, multiply by the stiffness matrix, and then transpose of that. Then you will get one. If the quantity is positive, you always say the system is positive. Okay, so this is identical. Only thing is here it is all differential. Okay, I am not getting into spring mass damper type of systems and then try to derive the equation and show both are same. Okay, it's similar. All right. Now what we will do is, if they are self-adjoint and positive definite systems, eigenvalues are positive. Okay, all eigenvalues are positive. Real positive. Real positive. That is the key. Okay. All eigenvalues are real and positive. That is why if the system is, now I am just describing, if the system is non-self-adjoint, you can't guarantee. They may be real, they may be complex, they may be anything. Okay, that is why you first check all your operators whether our problem falls into this category. If they fall into this category, that means I have a solution of this type. I have these quantities are all positive. Okay. Only thing is, now the question is, how do I go and get them? That's a different part. But it is guaranteed that they must be positive. That is why self-adjoint and positive definite, both are important. If it is simply self-adjoint, that is only real symmetric matrix. The real symmetric matrix, you will get real eigenvalues. They may be positive, they may be negative also. Okay. Whereas if it is positive definite, you can show that this will be greater than 0 for our problem. That's why I would say I left it to you. You show that for our given operator, show that this is greater than 0. Okay. Then you know that these things must have real positive eigenvalues and some corresponding eigenfunctions. Okay. Is it okay? But these are all shown with comparison functions. Okay. Now let us prove one more condition, which is the orthogonality principle. Okay. That's a bit, it will look a little messy, but it's all right. I thought I will show that. Okay. Orthogonality of eigenfunctions. Okay. Consider lambda r and lambda, sorry, not lambda, you can take it omega square itself. I think that is better. Omega square r, omega square s. I may, for simplicity, I am writing it as lambda r, lambda s. Okay. Just for, because I am going to use only, not omega, I will use lambda r, lambda s. I am just denoting them. These are two eigenvalues. Corresponding eigenfunctions, please understand, I am using eigenfunction now. We will denote as W r and W s. Okay. These are the two functions. Now you know that eigenfunctions must satisfy my equation. So I will write L W R is lambda R capital M W R. Similarly, L W S is lambda S. Okay. Now let us multiply this by Ws, this by Wr, because please note that this is operator. So I am multiplying before, pre-multiplying and then integrating. So I will do integral over the domain Ws LWR, and then I am subtracting this. So I will put minus WR LWS D domain. This is equal to, again you have to do the same thing here, lambda R WS M WR minus lambda S WR M WS D. Okay. This is the condition. Only thing is, now I have to do some algebra. That algebra is, you know that they are LM, they are all self-adjoint, etc. You need to go and what you can do is, self-adjointness, we have defined a long expression. What was that expression we defined? That was the, we wrote the self-adjointness, this one. U L V D D plus summation I K plus 1 P U B I V D S. This is over the domain, this is over the. We wrote this is equal to, again, D V L U D D plus summation K plus 1 to P V B I U D S. Okay. We wrote earlier this because now they are self-adjoint, they are this. Now what I can do is, instead of U and V, you have WS, WR. Okay, which means I am replacing here this by WS, WR. U is W R, sorry, this is WR, this is WS. Because comparison functions, but they are self-adjoint. They have to satisfy the boundary condition. Eigenfunctions also will satisfy that. And then you take these terms, this you bring it to the left hand side. Okay, that means this particular expression, you can write it in terms of BIs. Okay, that is what you will do now. So you will write this is also equal to, please note that I have taken the left hand side, this I have brought in and I am replacing. Now I am writing summation I running from K plus 1 to P this is Bi U V, and here V is WR. So WR Vi Ws minus Ws Bi WR Bs. Okay. Similarly, what we had another relationship, which was we had this relationship, right? So I can also write that as this is one, and okay, before I go further, yeah. You can write from here Ws L WR minus WR L Ws. Okay. What you can write? You know, these are all from here. Please remember, I am substituting for BIWS and BIWR as correspondingly, because that WS I must put corresponding S. Okay. This I am going to substitute there. That will become, what will be that? This is essentially summation I running from k plus 1 to p. WR will remain as WR, because that BIWS should be omega S square CIWS. Omega S square I am calling it as lambda S. Okay. WR CI WS. Same thing here, minus WS remains same, BIWR, that is again lambda R WS BIWR, not BI, CI, right? CI DS. Okay. Now I have a relation this to this. Next, I erase this part. I think this is, oh no, I will keep this because everything is important. Okay. Next, what I am going to substitute is, I will take that term. Okay. I am going to substitute here LWR is what? From here. Then what will happen? This term domain, please understand, that is the domain WS, wait a minute, LWR. LWR is going to be lambda R MWR. So I am going to write here lambda R. No, this is this side, that is different. Oh, okay, then these two are equal. That is all, you can take it. Okay, I am sorry. Yeah. Maybe I can rewrite, okay, that's fine. Maybe I'll write it again so that that becomes clear. Okay. Domain D, yeah, that is there. Lambda R Ws M Wr minus lambda S Wr M Ws D dd. This is equal to this quantity. Okay. Now what you do is you have to do some substitution, because from this equation you have to do some substitution. Let us write this equation u as Ws. So I am going to replace this here Ws, and this is Wr, and here also u is Ws, right? This is Ws, right? V is Wr, V is Wr, u is Ws, Wr, Ws. What I am going to do is I am changing, I keep this term, I transfer all the terms to the right hand side. Then what will happen? I will have integral d Ws M Wr dd is equal to integral Wr M dd over the domain plus summation I k plus 1 to 1, sorry, k plus 1 to p Wr Ci Ws minus this term will come Ws Ci Wr ds. Okay. Lambda r. Okay. Now what I have to do is I take this term, this is integral Ws M Wr over the domain. I will simply take this entire term, put it here in this place. I am replacing, please understand, I am replacing this entire term in a particular place. Okay. When I do that, I will write my final, because maybe I will erase this part, because this is going to be a little link, yeah. Substitute here, this will become, that equation is becoming lambda r Wr M Ws. Okay. And then you already have this term lambda s W R M W S. This whole thing is the domain. Then you have to add this term also. You will add plus summation I k plus 1 to p. This is over the surface. Again you will multiply lambda r W R C I W S minus W S C I W R D S. then this is you have to equate to that term. Okay. So I erase this part. You are equating to summation I k plus 1 to p lambda s w r c I w s minus lambda r w s c I w r d s. Okay. You have here lambda r w s c I w r, lambda r w s c I w r. So those two terms will cancel out. Okay. Leaving behind, please understand, leaving behind, I am now erasing everything, put it in a very compact form. Okay. The compact form will be, because this is same, WRMWS, WRMWS. You will have integral WRM S dd is over the domain. Here you will find WR CI WS, that is common term. This will come left side. So you can write plus summation I k plus 1 to p WR CI WS DS multiplied by lambda R minus lambda S equals 0. Okay. Finally, that's what you are going to get. Now you say, if my eigenvalues, which are lambda R and lambda S, if they are different, okay, that means this minus that is not 0, which implies this term must be 0. Okay. That is why you say distinct eigenvalues. Distinct. But suppose you have repeated eigenvalues, then what will happen? Then for this self-adjoint positive difference system, you can have distinct eigen functions. Even though the values may be repeated, but you still can have distinct eigenfunctions which are orthogonal features. Okay, that is why now you say lambda r is not equal to lambda s. This is it. If it is equal, then what? Then also for this class of problems you can get the orthogonal eigenfunctions. They are distinct. So the orthogonality condition is defined by this expression. Okay, that is integral WR M WS dd plus summation I running k plus 1 to p integral surface WR CI S ds. This is, you write it as delta r, because it's like when r equal to s, you get 1. How do you get 1? Can you guarantee 1? That is where you now talk about hey, I can, these functions, I make them normalized, okay, such a way when W R M W R, W R C I W R, it is equal to 1. That means I am normalizing the eigenfunction, okay. Even if you don't normalize, nothing will happen, problem will be fine, because this is called orthogonality of eigenfunctions, okay. Orthogonality condition of eigenfunction. Now we have defined it over M. You can also define it for, but please understand your M is sitting here, okay, and your Ci is there. That's why this is only those boundary conditions which have omega square sitting there. That's why if all of them are 0, 0, omega square is not in the, you will not get that term. Now what you can do is, you can go and substitute for MWS, okay. Suppose I multiply that equation by lambda s, just because that is, I can put it lambda s, I can multiply, then lambda s MWS is LWS. So I can replace this by LWS. So that also I can write it D WR LWS DD plus summation, because here that's going to become WR BI WS, okay, equals lambda S delta RS, okay, and these are my orthogonality conditions, okay. Now you have the complete set of, I would say, conditions which you have developed. No, 0 means I am putting when WR equals WS. Then what is that? Okay, why am I writing delta RS? I am putting delta, see, when WR equal to WS, then you cannot say lambda R, basically lambda R minus lambda S is 0. Lambda R minus lambda R, the other term need not be 0. Okay. But if you have repeated eigenvalues, then you can have, yes, orthogonal eigenfunctions for these types. That can be proved, because I am not getting into those proof, okay. Because if you do theory of vibration, normally it is given in the discrete system. You can give the proof, self-adjoint system, self-adjoint positive, everything, you put it positive definite, then you can show that yes, they will have orthogonal eigenvectors, okay. Now you have the proof for this. But please understand, these are only for eigenfunctions, not for comparison functions. Only eigenfunctions are orthogonal, not comparison functions. So if you want to get exact solution, only very special case you can have exact solution. But that is like an ideal case, uniform beam, okay. You put a uniform beam, put a cantilever or simply supported, you can get nice solution, but is not a uniform beam, and you can have masses attached at different locations. Then the question is, you cannot get a closed form nice solution. So the whole technique is, how do you get approximate solution? Okay, this is where what we will do is we will study that part later, because I am not going into details of this part, because this you must have done vibration course, theory of vibration if you have done, or this is also comes, they call it structural dynamics. If you do the structural dynamics course, there it is taught. Because I just want to spend 1 hour on this. I will immediately go for how do you get the approximate solution. Okay, that is what our aim is. All right. So that we will do in the next class.